You've probably heard of the Heisenberg's uncertainty principle. The more you know about a particle's position, the less you know about its momentum. The popular explanation is that the particle has a definite position and momentum, but when we measure the position of the particle by shooting particles at it, it changes the momentum of the particle and thus we don't know the momentum. Although this is easy to understand, but this is not the uncertainty principle, but rather the measurement problem. The real Heisenberg's uncertainty principle is actually the consequence of superposition. Before being measured, a particle exists as all possible positions at once. Each position is assigned with a probability, and when we measure the particle has to choose a definite position corresponding to the probability. The superposition is gone. We could instead represent these superpositions as a wave with the amplitudes of the wave representing the probabilities. In fact, the superposition nature is why people say particles behave like waves. The wavelength of the probability wave is related to the particle's momentum. It's actually all because of special relativity. The faster an object moves relative to you, the more it will contract in its direction of motion, also known as length contraction. Let us now apply this to our probability waves. The more momentum an object has, the faster it moves, resulting in a squished wave. This wave has a shorter wavelength, allowing us to write this. This does mean that different observers see different wavelengths. Now that we've understood that the particle's position and momentum can be described by its probability wave, we shall think of a particle with a definite wavelength and thus momentum. The amplitudes of the wave is the same everywhere, and we are completely uncertain of its position, as it has the same probability of happening anywhere. Let us now make a probability wave that only allows the particle to be in a few positions. The position is now more localized, but where is the wavelength? Is it this, or this? We have lost certainty of the wavelength and thus the momentum by trying to localize the wave. If we allow a certain momentum, we would be uncertain of its position. Similarly, if we constrain its position, we would be uncertain of its momentum. In both cases, the particle itself had to lose certainty of either position or momentum. We now know that the Heisenberg's uncertainty principle isn't that the particle itself has an exact momentum and position that we can never know. It's that the particle itself doesn't have a certain momentum or position because of the wave-like nature from superposition.